So in the A model, we have some symplectic manifold. Then branes are Lagrangian submanifolds of X. Open string states well, the way people would normally write this in the math literature is it would say that these branes form a category called the Fukaya category. So these are Halms in the Fukaya category. And the space of such homomorphisms is called a Floer cohomology group. So morally speaking, this space is some kind of semi-infinite cohomology of the space of paths in X which start on L1 and on L2. So this is, as far as I'm aware, there's no proper definition along these lines, but this is an intuitive idea of what this space is that people use in the field. But we're going to be even a bit more naive. So for us, the open string states from L to L, we'll mostly treat them just as the space of differential forms on L, and then plus stringy corrections, which we will mostly ignore. So there's going to be a contribution from the space of, think of this space of paths.
I totally missed your first slide. I'll be more careful next time.
Oh, it's
Can you bring it down and then I'll take a picture?
Oh, okay, okay.
I forgot that they disappear after the video.
Oh, sorry about that. Let's put a slide down. Maybe I'll move over here. Oh, they really disappear into the ceiling, don't they? Yes, absolutely. So for us, we'll be kind of naive, and the open string states will be just differential forms in L, which we think of as the constant paths starting and ending on L and not going anywhere. And sometimes we have to worry about kind of stringy corrections from long paths, but most of the time we will not care about those. Now, what happens if we have the product of a symplectic manifold and a complex manifold? Then we can consider a mixed AB model. Yeah?
In the case where L1 and L2 are distinct, you're not sort of giving any, there's no corresponding naive definition.
Oh, there is, yes. L2, it's just differential forms on the intersection, assuming that they intersect nicely, plus stringy corrections. And the differential will be correct. The differential will be corrected too, but we're not worrying about that too much.
Nice here means
clean, so that the intersection is a union of manifolds and not something crazy. The only thing I don't remember is that there's a degree shift, and I just don't remember what it is.
So floor cohomology is the exact result or the tree level result?
Everything is tree level. But the only difference is whether we include the the contributions from holomorphic disks with non-zero area or not. Flow cohomology is the result which includes disks with non-zero area.
Non-zero?
Area. Non-constant disks, they give a contribution to the differential. And we'll also have...
So these are the alpha prime corrections?
Yes, exactly.
So flow cohomology does not include
No,
alpha prime corrections?
no, flow cohomology is the one with the alpha prime corrections. The space of differential forms has no alpha prime corrections. So we'll see maybe an example in a minute of how this works with T-duality. So if we have a mixed AB model, we might have X, which is symplectic, and Y, which is complex. We also need it to be Calabi-Yau. The symplectic manifold does not need to be Calabi-Yau. We can consider a mixed string theory. On X cross Y, which is the A model on X, and the B model on Y. In this mixed string theory, branes, well, a nice class of branes, there are actually more, which we won't worry about so much. Of a Lagrangian inside of X Z inside of Y, holomorphic submanifold.
Is this going to end up being some sort of just like tensor product?
Yes.
In some sense of theories?
Yes, and it's a tensor product of the categories, which is why I'm not completing the tensor product, because that's why I'm only restricting to these ones.
But in particular, like these branes that you just wrote down generate.
Yes, yeah, exactly. So the open string states. So without including the alpha prime corrections, are just the tensor product. Tensor, well, tensor whatever the open string states on Z are. But we saw last time that a pretty good approximation, in fact, we can describe the open string states on Z. We studied this in flat space. It's the Dolbeault complex on Z with coefficients in the exterior algebra of the normal bundle. So just a tensor product of A model open string states with B model open string states. So as an example, so consider or to K, which will be an A model direction, cross C5 minus K B. So this is some 10-dimensional topological string theory, and we will see later that if K is, let's see, odd, then this is one of the twists of 2A, and if K is even, it's a twist of 2B. So these examples will be very relevant for our story. So what do we find if we put some brain in here and here? So as we take a product of r to the k times c to the l to k, and this is inside c to the 5 minus k, then open string states so there are functions on this space and then I must join a number of odd parameters, some coming from the Durand differential there, some coming from the Dolbeau operator there, and some remaining ones coming from the fact that I take the exterior algebra of the normal bundle. And the differential, sum dxi by dxi plus sum dz bar I by dz bar I. Okay. Yeah?
I think I have 3 separate questions. One is, what's the number 5?
Why is it 5?
Yeah.
Well, 5 could be any odd number to make this to work, but string theory lives in 10 dimensions, and we wanted to understand string theory.
This is your favorite odd number.
Yes.
Okay.
5 and 3. Yes.
So question 2 is, the story that I've seen of the kind of category also has various like U1 bundles floating around that are usually left out in the first telling. Are you leaving them out in the first telling, or are they not here?
I'm leaving them out on the first telling. I'm also leaving out on the first telling the corresponding thing on the holomorphic side, which is I could have had a U1 bundle here. But notice that these are such trivial spaces that there isn't much room.
Okay. And then this is the like without stringy corrections.
Yes. So the real, that's right, without stringy corrections. So let's do the example we said last time of T-duality between type 2A and type 2B and how this appears. So for us, T-duality will arise when we take 2A model directions, which form a cylinder, and they can be turned into 2B model directions, which form a cylinder. And because this interchanges, whether K is odd or K is even, it interchanges 2A and 2B. So everything factors as a tensor product, as a product of A and B model directions. So we might as well, if we're going to understand T-duality, we might as well understand it first just on a cylinder itself. And then we'll just stick in the extra 8 dimensions, and they won't really change. So we'll just understand a cylinder. So. The cylinder is the cotangent bundle of S1, of course. And we're going to be interested in 2 Lagrangians. The fiber Lagrangian and the base Lagrangian. So the base one is just the circle, and the fiber one is an infinite straight line. So ignoring alpha prime corrections, the open string states for LF are just forms on LF That's just forms on OR. However, there are other open string states which we have to take account of to make T-duality work. And this is probably familiar to physicists. So what else can we do? We can consider an open string state which winds around some number of times and comes back to that same Lagrangian. So including alpha prime corrections, we find that the Floer cohomology, LF, it has a single state for every integer. Whereas, if you look at this guy, the other brane, that has no alpha prime corrections.
It's not really an alpha prime correction, right? It's just a different sector of the theory.
That's just a weird thing?
Classically, this sector exists.
Okay, maybe that's, I'm pretty poor at string theory nomenclature, so that's...
I thought alpha prime correction should have something to do with the curvature of the manifold, right? So if you don't have curvature, then...
Well, even without curvature, there can still be non-trivial holomorphic disks, which can contribute in like a non-local way to the product. So maybe you could say that this version of it is what you find in the field theory limit, and this is the string theory version. Because in the field theory limit, it has to be local in the brane, and this is not local. So doing corrections. Okay, so the other brane is that the naive local picture is correct. And we find that the Floer cohomology forms an LB, and this is equivalent, of course, to just differential forms in this circle. Now, yeah?
I am surprised that there aren't cancellations of the cohomology of itself when you actually include the positive area states.
Well, there's no room because everything is in even cohomological degree. The way mathematicians would normally explain this calculation would be to talk about the wrapped Fukaya category. So instead of thinking about long strings like that, they think about making your brane wind around at infinity. And then you would say you take L, and then another copy of L winding around at infinity. And you find that there's only things in even cohomological degree, so there's just no room for anything with disks. There's a paper of, I learned this from Mohammed Abizaid. So I think one of his papers.
Because I mean, there's like naively disks that you can, you can kind of try to fill in a disk, but you're just saying they're not going to.
That's in the wrong dimension, I think.
Could you also calculate it as like a self-exponent delta function at a point in S1, like in somehow in
Yes.
mod 1S1?
Not in D modules. That's a good point, though. It's because D modules. So we're having this discussion about the difference between field theory and string theory. D modules are a field theory thing. They're local. There's a sheaf of categories. Whereas these string theory things are not local. However, there is a version of the category of sheaves, which you can just take to be representations of pi1 in this case, and which you get the right answer. So in general, the Fukaya category of the cotangent bundle of M with the correct behavior at infinity, which were the one relevant for here, is going to be equivalent to the algebra of representations of the singular chains of the base loop space.
this guy was imagining as somewhere higher in the infinity structure.
I see. Yeah, it's these four things, right? Yeah. And then in the literature, but this equivalence, the basic brane is the fiber. Fiber at x goes to just the regular representation. And whereas the base goes to the trivial, the augmentation. So in the case we're studying, the base loop space of a circle is just a copy of the integers with no interesting topology. Kind of running out of room. The base loop space of S1 is homotopy equivalent to Z, so chains on it is the group algebra of Z. And then you can do what you said for both of these calculations and get the right answer.
Should this also be something like the category of representations of sort of like a shift of the homotopy groups as a Lie algebra?
That's right, because this algebra is a universal enveloping algebra of that, the other thing you just said, assuming certain nilpotence hypotheses which don't quite hold in this example, but but if you look at the two-sphere, then what you said would be true.
What do you mean by chains on something?
Pardon?
What do you mean by chains on something?
So in this more, I just mean, say, singular chains or simplicial chains. It's not going to matter. The category you get doesn't really care about the details of the model you use.
Chains on Z will be like choose each point some arbitrary number of times. So
yeah, each simplex in it, some linear combination of points and simplices, or if you prefer, you could choose a simplicial decomposition of this big space. Anything like that. It's pretty much the same as representations of the homology. The only difference is you might, if you use the homology, you might have missed some infinity structures. In this case, you don't, but in other cases, you might. Okay, so what's the mirror of this? Is this the B model on C star. There's two basic branes. Before, like the structure sheaf of C star and the structure sheaf of a point. And the way people expect T-duality in string theory to work, we take this fiber. When I apply T-duality, it turns into something which fills up the whole cylinder. And conversely, the base, so this should become by T-duality. And this should become by T-duality. The base. So we've just checked, and read it out again, that the open string states are the same.
So structure shape of a point is the D minus 1 graph?
Yes. But in the other four directions, which we're not talking about, it could be accompanied by something else. So it could. So OC star, this will just give me the open string states, which is just the Dolbeault complex of C star, whose cohomology is C adjoin Z and Z inverse, and structure G of a point will give me, remember the rule is to take the exterior algebra from the normal bundle, so we have one odd variable. Cohomology of a circle, and these match up with what we found over there. Okay, any questions?
In more general, that equivalence is true. Currently, we need
I believe there's a paper of Abu Zaid on the archive discussing this. I think it's always true that the Rapid-Chi category of any manifold is this.
I mean, do you have any physical explanation?
Well, the physical explanation is just Muhammad's argument, which is for any object of the Rapid-Chi category, you can take harms from that to any fiber. That's a functor. Once you compute the endomorphisms of a fiber, and it seems more. I mean, it's clear that the endomorphisms of a fiber should have something to do with the loop space, the base loop space. We already saw that in the circle, so that's not crazy.
So you convince yourself that your category is generated
By fibers.
fibers.
Yeah, or one fiber. I think that's probably the hard part of the argument. Yeah.
You sort of also have to convince yourself that your category is not some sort of weird category.
What do you mean?
You have to convince, well, I guess you have to convince yourself that like a fiber is compact with someone in that category.
Does G-string play a role in all of this story?
G-string? Yes. But so it will become then on each brane there's a field theory, and the coupling constant for that field theory is G-string, or square root of G-string.
Is there any problem with G-string at large?
Yes. I mean, I don't know what to do. I mean, this is a perturbative description. Yeah, I mean, maybe there are situations where non-perturbative things can be seen, but in general, it's just perturbation theory.
What is the augmentation of it?
Oh, well, if I have the base loop space, it's that algebra is naturally augmented. There's a map from the chains in any space to chains in a point, just by pushing forward to a point, and that's the augmentation. It's an algebra augmentation in this case. It's algebra homomorphism. Let's see. So if we lift this to 10 dimensions, we find that we consider type 2A can be twisted give the A model on Norcross S1 and 2B can be twisted to give the B model on C star is the B model on C4. Now we can take a brane here, and a D brane in type 2A will give a product of a Lagrangian brane here times some brane in here. So if I fix some Y inside of C4, holomorphic submanifold, let's say ck, some linear embedding, then I can take a brane which looks like or times a point times ck. This is a d2k brane in type 2a, and this discussion says that when I apply t-duality, because I'm not dropping the circle, when I apply t-duality, I find the full cylinder. And this is a d2k plus 1 brane. It's the usual string theory picture, of course. Similarly, if we take a point, say a point in OR, times S1 times CK, which is again a D2K brane, and apply T-duality, becomes a point times CK, and it's a D2K minus 1 brane. And let's see. I think as I mentioned last time, you can, with some work, derive from first principles the fact that the open string states here describe the fields of the supersymmetric gauge theory in this dimension that lives on that brane. So this really what we're finding really does match up with the physical string, with how T-duality works in the physical string. Okay, any questions? No? Sorry, that's disappearing up there. So another topic I wanted to see if we could understand today would be space-time supersymmetry. So to do that, we need to understand a little bit about the closed string sector of the theory. Suppose we have a symplectic manifold. Then the space of closed string states well, there's the same distinction we had before. There's a version of the space of closed string states, kind of a naive first approximation, which is a sheaf on this manifold. So the first approximation is forms on X. The first approximation, which in physics language maybe is like the field theory limit. And then there's a more fancy thing, which is the symplectic cohomology. And for the B model,
what's the relation between symplectic cohomology and quantum cohomology?
well, quantum cohomology is ordinary cohomology with some extra structure. So I haven't really discussed the extra structure. So quantum cohomology is this. But if I have a non-compact symplectic manifold, then the quantum cohomology is not really the right thing. The right thing is the Fourier cohomology of the loop space. This is a better match, the Hodgson cohomology of the Fukaya category, for the same reason. So in the case X is a cotangent bundle, a result of Viterbo says that the symplectic cohomology of X is the homology of the free loop space of X, of N. So we get these contributions from circles winding around M. And this you can check that this is the Hochschild homology of the base loop space, so it matches the form of properties you expect.
Should there be a constant correspondence between the vertex operators of the closed string states and symplectic homology?
Yes.
But do we know how to construct all the vertex operators for the closed string states?
Of the topological string?
Yes.
I think so, yeah. Yeah.
I mean, is that how I would derive this result, or is there another way to derive this result?
No, the way you derive this result would be, well, first you assume the state operator correspondence, and then that's how you define what all the vertex operators are, and then you look at the solutions of the equations. You look at the phase space, the solutions of the equations of motion on a cylinder. You find that's the loop space of X, and you look at there's some. Then you apply there's some flow, and you realize what you should end up with is the Morse cohomology of the loop space, following Witten's work in the 80s. And that's how that's defined. So the closed string states in the B model are, let's say, Y. So it's a Dolbeault complex on Y with sections in the exterior algebra of the tangent model of Y. So if locally, if Y is equal to CK, this is like functions on CK that join dz bar I, also del J. So we join an odd variable corresponding to every tangent vector, homomorphic tangent vector.
Can there be two oscillators in the closed string case?
What's that?
There should be two oscillators in the closed string case.
Oscillators under the Virasoro representation?
See, this way you construct states is using alpha mu and alpha twiddle mu.
Oh, but it's topological, right? It's topological on the world sheet. So there's no dependence on that.
I thought the differential forms were coming because of the alpha mu in the open string case.
I mean, I don't know.
The index of the differential form was coming from this.
I don't know the physical string so well, but like the way this is set up, like the action is just manifestly topological, and that there's no dependence at all on the derivatives of the world sheet. Okay, so there's one more constraint, which might seem from the physical string to be a little funny. So in the physical string, you might look. So what I've really written down here is the states of the field theory. So in the physical string, you have a 2D CFT coupled to world sheet kind of supergravity, superconformal gravity. And then you should take the states of the field theory, and then you only want those which are preserved by, which are compatible with the symmetries of the world sheet. So here the same thing happens. We need the states that will be relevant will be those which are preserved by certain symmetries. But the symmetry that plays a role is a little bit funny. So we're looking at the states of the TFT on a circle. A small rotation acts in a q-exact way on the states of the TFT. Sorry, I think my brain is fading, but what always happens in this situation is that we can find, on the Hilbert space of states, we can find an odd operator which corresponds to integrating. So like del theta is equal to q, say q theta. Then the integral q theta, this is an odd operator on the space of states.
Okay, like too closed up.
Yes. Just because if I integrate this rotation, I come back to where I started. So, and we want states which are invariant under this.
What does that want correspond? Like what? You're allowed to want whatever you want, but why would I want that?
Because this is part of the symmetries of the. If we were in the physical string, you might say, oh, we might look at superconformally invariant states, and this might be part of the superconformal algebra. So states should be invariant under it. Here, the fancy way to say it is we have an S1 action, and this data is lifting it to an action of S1 to RAM, and we want an S1 to RAM invariant states, which seems a very reasonable thing to do.
This is something like saying I don't really want sort of a string. I want a string up to kind of I want an unparameterized string.
Yeah, exactly. So I want to be able to stick these states in at points on a Riemann surface, not at points with a framing. And this is the data I need to be able to do that.
So integral d theta should be 2 pi, right?
What's that?
Integral d theta
Yes.
should be 2 pi, so it's not closed.
Hold on, am I doing this wrong?
No, the integral of del theta is the identity map. Del theta is the rotation in S1. So this is del theta is the vector field, but if you take the group S1 and integrate the generator of that group, come back to the identity.
Yeah. There's a very good chance the formula I wrote down is wrong. I'm just feeling a bit tired and I haven't got it in my mind. Well, what is this operator? So let's first have an idea of what it is on the A model side. Morally speaking, well, let's assume in the cotangent bundle case, we have this example. So then, symplectic cohomology of X is the homology of the loop space of M. There's a circle rotation map like this, by taking a loop and appointing the circle and rotating it. And this gives a map on the homology of S1, tensor the homology of the loop space, the homology of the loop space. If I take the generator, which is the fundamental class, this gives us an operator HK LM to HK plus 1 LM. And this operator is this operator. So you can see what this operator does is it takes a cycle in the loop space, and I look at the cycle of one dimensional higher obtained by averaging how I rotate it. But to be honest, most of the time when we ignore these non-local contributions and just look at loops near the constant loops, this is not going to do anything, just because constant loops are just fixed by this operation. Now in the B model, so the odd operator on this space is, well, in coordinates, Zi, it looks like, so this algebra, it's called the polyvector fields, sections of the bundle, the exterior algebra of the bundle of the tangent bundle. So it has odd generators, one for every coordinate. So I take the derivative of a coordinate function, then the derivative of one of these odd generators.
This circle is on the world sheet or in the space-time?
This circle is on the world sheet.
Okay, so you want invariance just because of diffeomorphism invariance?
Yeah, more like a kind of super diffeomorphism invariance of the world. This is why it's an odd.
So Q is not the BRST charge?
It's the BRST charge of the topological theory, which is, for example, if this TFT
This includes the supersymmetry.
includes the supersymmetry, exactly, yeah. Okay. So this operator will play an important role, and it's called divergence. For the obvious reason that if I take a vector field, it gets sent to its divergence, literally, but it might take a section of the exterior square of the tangent bundle and produce a vector field. And you can check that del squared is equal to 0. So as an example, let's revisit the case of the cotangent bundle of the circle, see where these operations match.
I know you did, like, just because of the word divergence, certainly that's one of the places the Claudio structure and Y appeared. Did it already appear earlier?
Well, I wrote down the space of open string states, but I also said we needed to have an algebra structure and a trace. And the Claudio structure appeared in the trace. It was the A model. I take the cotangent bundle of the circle, then the closed string states are, as we saw, the homology of the free leaf space of the circle. Now, the free leaf space of the circle has a bunch of components. It has a component indexed by the integer, but each one also has the only homotopical data left is where the base point goes. So it's homotopy equivalent to z times s1. So this homology of this free leaf space of the circle, it's a bunch of copies, an integer's worth of copies of the homology of z. So I can write this as an algebra y of z, z inverse, corresponding to the generators of the integers, and then I will join a single odd parameter. So epsilon is some odd parameter. Now, the B model, if I take y to be C star, the closed string states the double complex C star with coefficients in the exterior algebra of C, which is the tangent bundle. So passing to cohomology, I find homomorphic functions on C star join an odd parameter, which I'll call del. Okay, so let's calculate the divergence operator here. So del measures the failure of some function times del z to preserve. So preserve the volume from dz mod z. So I'm going to normalize this guy. So there's a z del z. That should be what we find, that del of f z del z is z of f prime. So we want to match up these two spaces by sending epsilon goes to z del z, and then we have to check that the S1 action does the right thing.
Sorry, on the left-hand side, did you say what it was in multiplication by epsilon?
I didn't say what it was yet. We have this geometric description in terms of taking a loop and spreading it out, but we haven't calculated what it does in the spaces. So I think there's a priority shift going on under this isomorphism, which I must be missing. So A model, the A model side, say z to the n, I think should get sent to z to the n times z del, and z to the n epsilon should get sent to z to the n. So we have this map here. We have this map here. So here, this corresponds to a circle, which, this is a zero chain. It's a circle which just wraps around n times. And then I spin it. You get a one chain in the moduli. I get a one chain, but this epsilon is a class on the homology of the base. So there's a factor of n here. Because if I take the base point in this guy, and I spin it around, it wraps around n times here. So these match up.
What is the downward arrow? What map is that?
Oh, the downward arrow is this operator coming from the S1 action on the world sheet.
It's the integral of q theta?
Mm-hmm. Yeah. Okay, so we sort of see that the A and B, the A and B model states match up, and they match up in a way compatible with this S1 action. I've dropped some details. So what I want to talk about next time is how to try to match up. We expect, for example, that if this was C5, that inside here should be things which look like the fields of type 2b supergravity. And I want to try to explain how you can sort of see that, and how you can also see some remnant of the supersymmetry action on these topological strings.